Good evening, everybody.
Hello.
Okay, still got some folks joining. Hopefully everybody can see the screen where we're going to pick up from where we left off last time, talking about horizontal shear. Is the screen available for everybody?
Yes, it is.
Okay, 10-4. So before we jump into tonight's lecture, does anybody have any questions they would like to ask about anything? Okay. Before we jump into this, at my company, whenever we start a meeting off, we always do a safety moment or a value moment. It's just something that we adopted so that you're always thinking about safety, at the beginning of every meeting. I had a value moment at lunchtime for the last few days. I've been watching Netflix during lunch, and I've been watching about the Challenger space shuttle disaster. I don't know if any of you guys have caught this yet or seen this on Netflix. Um, for one thing, it's really, really sad what happened with the Challenger back in 1986. For those of you who may not be aware, basically the Challenger was the first space shuttle that we had a disaster on. And something like 73 seconds into the launch, the whole orbiter just exploded. And so the value moment about this is they're really kind of digging into all the engineering that went into the space shuttle. The space shuttle has been said to have been the most complicated machine ever built by humankind. Just millions and millions of pieces and parts and working whatever. But apparently, watching this show, you had subcontractors that were responsible for different portions of the shuttle. So one company made the actual shuttle itself, another company made the engines for the shuttle. One company was responsible for the solid boosters that are on either side of the shuttle. And that company was getting very concerned about these O-rings that sealed off one segment of the booster from another segment of the booster. And they were seeing signs of failure of these O-rings, of these hot gases kind of burning or trying to burn through the O-rings. And what made the problem a lot worse was the colder it was at the time of launch, the worse off these O-rings would perform. And so the point of the value moment is that now we're getting from the politics, and we got Congress who's demanding so many flights a year, and NASA is asking for so many billions of dollars. You get down to like a handful of engineers going, wait a minute, this isn't working. And they tried to tell them that this isn't working, and they basically got overruled by pressure from NASA administrators and Congress people saying, we got billions of dollars on the line, make it fly. And they were overruled. They said, no, we don't think this is safe. And saying, well, it'll be fine. And then 7 people died. So I don't know, does this all make sense? As engineers, sometimes we have to have the courage to throw up the red flags and say, if it ain't working, if it ain't right, it ain't right. Doesn't matter how much money it costs to delay it or to fix it. If it ain't right, it ain't right. So that's, I guess, my value moment for today. Any questions? Okay. All right. So going from space shuttle disasters to just a 2x4 in horizontal shear seems a little anticlimactic, but here we go. We were doing this example where we were looking at a beam that is 2 inches wide, 4 inches high, and we were looking for the horizontal shear. The first part of the example that we did is we found the horizontal shear across a plane 1 inch above the neutral axis. Now we're going to find the horizontal shear at a plane that is right at the neutral axis. So in order to do so, we need to calculate Q. Q is the first moment. So to find Q, I need to find A prime, the area of the area above or below the line that we're finding the horizontal shear upon. And so A prime is going to be 2 inches by 2 inches, or 4 inches square. And I need to find Y bar prime, the center of gravity of A prime, to the center of gravity of the whole section. So in this case, Y bar prime is going to be half of the 2-inch high A prime area. So Y bar prime is 1 inch. Q then is A times Y. 4 times 1 is 4 inches to the third. If I go about it from the other side, remember what I said is that wherever your cut plane is, that Q is identical whether you take it from above or from below. And in this case, it's trivial to see that because it's exactly the same area above and below. So I got 4 inches squared, Y bar is the 1 inch, Q is 4 inches to the third, but these have to be equal regardless if you're taking Q from above or below your cut plane. So now if the shear is 10 kips, let's find tau. Tau is my horizontal shear. And I need my moment of inertia is 2 inches wide, 4 to the third over 12, 10.67 inches to the fourth. B is equal to 2. That's the width of my shear plane. So VQ over IB is 10 kips times my Q of 4 inches to the third over 10.67 inches to the fourth over 2 inches wide. That gives me 1.87 KSI. That's my horizontal shear due to a 10 kip shearing load. Any questions on that? Okay, so let's take it one step more complicated. Instead of a simple 2x4, let's look at a T shape made out of two 1x4s. This is the same shape we've done before. So the first part is I want to find the horizontal shearing stress at the underside of the flange. That's right across there. So I can actually, I don't remember if I drew it in or not, so I'll just draw it in temporarily. We're looking for the shear across that plane right there. So to do so, I need to find my center of gravity for the whole section. Center of gravity for the whole section is the area of each piece times its centroidal distance. So I got 1 times 4, halfway is 2 here, plus I got 4 times 1 times halfway is the 4 plus a half here, divided by the total is 8. I get my Y bar is 3.25 inches from the bottom. So now this is my shear plane, like I said. So if I look at the area above the shear plane, that's the hatched area here, then A prime, actually I did Y first, didn't I? So the distance from here to the bottom of the shear plane is 3/4 of an inch because I have 4 inches minus 3¼ inches to the center of gravity. So that distance right there is 3/4 of an inch. A prime is the area of the 1/4, so that's 4 inches squared. Y prime is going to be half of the thickness of that board plus my 3/4 inches, okay? Y bar prime is always measured from the center of gravity of A prime to the center of gravity of the whole section. It's not measured to the cut plane, it's measured to the center of gravity for the whole section. So that is half the thickness of the bar plus the distance from the bar to the center of gravity. And that's 1¼ inches. Anybody have any questions about that? The definition of Y bar prime? All right. So then Q is A prime times Y bar prime. 4 times 1¼ gives me 5 inches to the third. That's my Q for a cut right at the bottom of that plate. Now, if I look at it from below, I should get the same value, right? So looking at it from below, that Y minus 3¼ inches, that's still 3. I'm not quite sure why I did. Oh, no, I do need that. Okay, so this distance here is 3/4 of an inch. A prime is the area of this whole plate, which is 4 by 1 or 4 inches squared. And Y bar prime is going to be 3¼ inches is this distance minus half the distance of the board, which would be half of 4 inches. So I get 1¼ inches. So Y bar here is 1¼ from the center of gravity of the whole section to the center of gravity of the hatched area is 1¼ inches. And so Q is equal to the same 5. That's how you check this. It should be exactly the same from the top or from the bottom. Okay, so if I put a 10 kip shear on this section, what is tau? Moment of inertia. I have 2 pieces now, so I have 1 times 4 to the third over 12 plus the parallel axis theorem is 1 times 4 times 3¼ minus 2 squared. Plus I have the top board, which is 4 wide by 1 high, plus 4 times 1 centroid of the top board minus the center of gravity of the whole assembly squared gives me 18.17 inches to the fourth. B is equal to 1 inch. Go back here just a second. My shear plane is right across here, and that's 1 inch wide. That's why B is only 1 inch in this case. It's not 4 because you don't have contact across that whole 4. You only have contact between these two across this 1 inch wide shear plane. So B is equal to 1. Tau, the horizontal shearing stress, is VQ over IB, which is 10 kips times 5 over 18.17. B is 1 inch wide. And your horizontal shearing stress is 2.75 KSI. Any questions on that part?
How did you get B again?
B is defined as the width of the material resisting the horizontal shearing stresses. So if you look at the diagram, B, the only part connecting this piece to this piece is right through here. So B, that's your horizontal shearing plane. That's the plane that's going to shear if the assembly failed in horizontal shear. So if the cut plane is right here, then B is 1 inch wide. If the cut plane was up here, then B would be 4 inches wide. But here it's only 1. Anywhere down in here would still just be 1. Does that make sense?
Yeah, thank you.
Okay.
I have a question.
Okay.
For y prime bar, does it
Yeah.
always equal to the distance of the neutral axis to the centroid of the shape?
It is always from the center of A prime, which is that red hatched area,
Mm-hmm.
to Y bar, the center for the whole shape.
Yeah, so that's the neutral, technically like the neutral axis, right?
The neutral axis for the whole shape.
Yeah.
Yes. Uh-huh.
Okay.
Yep.
Okay.
All right. So we're going to do this again, only this time I want to know what my horizontal shearing stresses are at the center of gravity. So that means what is the horizontal shearing stress across this section right there? Okay. See how that's different than what I asked before? Before I wanted to know what's the stress across the plane here. Now I'm asking what is the stress across the plane here? The procedure is the same. You first have to find your center of gravity for the whole section, which is 3¼ inches. And then you have to look at A prime. You can look at it from above or below. Looking at it from above, I find that, okay, I'm still finding that this little segment right here is 3/4 inch. A prime, now I got 2 pieces, so I labeled them A prime 1 and A prime 2. A prime 1 is the top plate, which is 4 times 1, 4 inches squared. A prime 2 is this little segment right in here, which is 1 inch wide and 3/4 inch high. And that then 3/4 times 1 is 0.75 inches squared. So actually, I'm not going to add them together just yet. So now Y bar prime 1 is the distance from the center of gravity to the centroid of the top plate, which is the 1/2 of 1 plus 3/4 inch equals 1¼ inch. And then I got Y bar prime 2, which is just halfway to this segment right here. So this segment is 3/4 inch high. So the distance from the centroid to the center of gravity of the whole section is half of that 3/4 or 3/8 of an inch. So Q is going to be equal to A prime 1 times Y prime bar 1 plus A prime 2 times Y bar prime 2. You add the two together. So 4 times 1¼ plus 3/4 times 3/8 gives me a total Q of 5.28 inches to the third. Any questions on what I just did there? So if I look at A prime from below, what should Q be? If I solve for it from the area below, what should Q equal?
The same.
The same, 5.28. So if I look at the area from below the cut plane, remember this is my cut plane right here. So I'm looking at the area above the cut plane and the area below the cut plane. I still have that same little 3/4 inch step right there. My A prime is going to be the 4 inches of the whole board minus that 3/4 inch step times 1 inch wide gives me 3 1/4 inches squared. And y bar prime is going to be half of that length right there. So this length again is 4 minus the 3/4 times a half gives me 1 5/8 is my y bar prime. Q is 3 1/4 inch squared times 1 5/8 inch gives me a total of 5.28 inches to the third. Thus again, confirming that we've done Q correctly.
Now, we have to do that every time we solve one of these problems, right? Solve for both of them?
That's a good question. Have to? No, no. It's a good idea. It's a double check. But no, I wouldn't say that you have to. If it's a lot of work to get one of them, especially on a test when you have limited amount of time, on a test situation, if I ask for what's the horizontal shear at such and such location, you may not have time to do Q twice. So I'm just going to leave it as a suggestion that it's a good way to check your work. Okay, what am I doing? Okay, I think this is a remnant. That's not supposed to be there. So find tau if the shear is equal to 10 kips again. And moment of inertia is the same as what we just did a moment ago. So that's 18.17 inches to the fourth. And B is 1 inch wide again. So tau is VQ over IB, which is 10 kips times 5.28 inches to the third, 18.17 inches to the fourth, 1 inch wide. And that gives me 2.91 KSI. That's my horizontal shearing stress through the center of gravity. Okay, so before I go on to the next topic, let me ask you a question. Where would you make a cut, do you think, that would produce the maximum horizontal shearing stress?
Anywhere in the at the top shape, like
Where it creates the T shape?
Okay, think about it this way. Horizontal shear stress, tau, is equal to VQIB, right? So as you decide where to make a cut for horizontal shear stress, you could make a cut. You can make a cut here. You can make a cut right here. You can make a cut right there. You can make a cut pretty much anywhere, right? But as you're making these different cuts, every one of these different cuts is going to produce a different horizontal shearing stress. So in this equation, what is constant? Anywhere you cut it, what is constant in this equation?
V and I.
That's right. That's exactly right. V and I are both constant. They do not vary depending on where you take your cut. B varies only by the width of what you're cutting through. So in this case, I only have two Bs. I have a wide and I have a narrow. Given that, the only thing that really varies constantly is Q. Q changes every time you make a different cut. See, all three of these cuts have the same B. This cut has a different B, but all four of these have a different Q. Q is in, what's the top one? The numerator? The bottom's the denominator? I don't know, it's
Yeah.
been a really long time. But in the numerator, if that's what it is, Q, the bigger Q is, the bigger tau is, right? So given that V is constant, I is constant, and for most of this section, B is constant as well, really the only thing that varies is Q. So where would you make a cut that would make Q at its maximum? Where's the maximum value for Q?
Far away from the neutral axis.
You think? Well, let's explore that. Let's go. Let's make a cut right there, far away from the neutral axis. Okay. So what is A prime? A prime is the area right there, that area. And what is Y prime? Y prime is this distance there. Distance from the neutral axis to the centroid of A prime. Well, is that going to produce a very large Q? Because A is very small. So that's not going to produce a very large Q. This one right here is actually the biggest Q possible. All the way to the neutral axis is the biggest Q possible, which is that number right there. If I go less than all the way to the neutral axis, Q is going to be something smaller. Like we found when we took the shear plane right here, Q was equal to 5. The maximum is right to the neutral axis, 5.28. If I actually try to make a cut up in here somewhere, you're saying, well, you add this much more area there, but you're taking that area away from this side. And what's happening is Y is actually getting smaller, so Q is getting smaller. So the answer is the largest possible Q available is taking a cut right at the neutral axis. So if I draw a side view, then actually, bear with me a sec. Let me do a side view lined up on the side of the section right here, right there. Okay, that side view. And right there, and that's the top, and that's the bottom. Okay. Now, if I plot out the horizontal shearing stress, in other words, if I do exactly what I did in this calculation, this example, only I do it like 10 times up and down the height of this section, then if I plot all those values, what I'm going to find is that the maximum is right at the center of gravity, and then it goes parabolic, and it goes to 0. At the very bottom of the section, there's exactly 0 Q. So you have 0 horizontal shearing stress at the bottom of the section. You have 0 at the top, but you're going to have this big step in here, just like that. Why is there a step right there?
That's where B changes.
That's where B changes. So the horizontal shearing stress just on this side compared to just on that side, the horizontal shearing stress on this side is going to be 4 times higher because B is 1/4 as wide. This is only 1 inch. This is 4 inches. So this jumps right there. I ran out of space, but this jumps by 4 times as high. So you're going to get a step in this diagram anytime B changes, but otherwise this is parabolic. And that's what your horizontal shearing stress plot is going to look like. Okay, any questions on that?
Will tau always be maximum at neutral axis? What if like B is the largest, or sorry, what would make it larger? Well, yeah, what if B was like the largest at the neutral axis? Then wouldn't tau be lower?
It could be. Yeah,
So
yeah. No, you're right. It could be. So I guess given a constant width, then tau is maximum at the center of gravity because Q is maximum at the center of gravity. But yeah, you could have some very strange mongoloid section that looks like that, right? And because this is so narrow, Q is small, but B is so much smaller, you could conceivably have a higher shearing stress here than through the center of gravity. Yes. Good observation.
that probably wouldn't be practical, right? Like, because normally like beams have the most of like are wider at the top and bottom for
Yes.
because shear stress, right?
Well, actually, the beams are typically wider at the top and bottom because it produces the most efficient moment of inertia with the least amount of material. Yeah, this would be grossly inefficient, but it's not impossible. I could be looking at a concrete beam and bending or a concrete footing or something like that that's not practical to make into a Y shape or an I or an S shape. Concrete is not practical to block out these areas. So this is what a concrete beam would look like. And then maybe you have wood or a steel strip that's attached to a concrete beam. So it's not impossible. Okay. Any other questions on these concepts? Okay, so here's the next concept. This is what's known as shear flow in built up members. So what we've done is B is in the VQ over IB equation to distribute a linear force into a shearing stress. So VQ over IB produces KSI. That's a stress. But I can also look at this as a shear flow. So instead of tau equaling KSI shearing stress, now I'm looking at Q. I took B out of this so that Q is a measure of kips per inch. Okay. Tau was a measure of stress, kips per square inch. Q is a measure of shear flow, kips per inch. Okay, so we can say that the force required is equal to Q, kips per inch, times S, which is a spacing of fasteners, where S is a fastener spacing. So F required would be the strength required per fastener, depending on the spacing of the fasteners. So you can turn this whole thing around and you can solve for Q, divide Q by the allowable load per fastener, and that will tell you what the required spacing of those fasteners needs to be. Okay, so as an example, what I've got here is sort of a T-beam that is made of wood. So this would be a 1.5 by a 10-inch high board. This is a 1-inch by 10-inch board at the top, and I got these two 1 by 3 runners on either side. And I'm going to connect everything together by nailing them. So I'm going to pound in nails horizontally from the runners to the top board, and I'm going to pound in nails from the top board into my web, essentially. And so what I need to know is with a given shear load and with a given allowable load per fastener, what is the required spacing of my nails? So I'm going to say, find the required fasteners at the indicated junction if the shear load is 700 pounds, which is not unreasonable for a wood beam of this size. I'm going to say that I have an allowable load of 100 pounds per fastener, or 100 pounds per nail, basically. So at first, this is my shear plane right here. And I need to know what is the spacing of the nails that crosses that shear plane. So in order to do so, I need to calculate what my shear flow is, my VQ over I. So I'm going to start with finding the area of the whole section. So I have two of these wings that are each 1 by 3. Plus I have a 1 by 10 as my top flange. Plus I have a 1.5 by 10 is my web. So my total area is 31 inches squared. Now I need to find the center of gravity of this whole mess. So the center of gravity is, this should be pretty familiar for you right now, but the center of gravity is the area times the centroidal distance to a reference point. I'm using the bottom of the beam as my reference point. So I have 2 times 1 by 3s, and then the centroidal distance is 11 minus 1.5. So I went 10 plus 1 is 11, back down halfway. So 11 minus 1.5. I have a 10 by 1 top board at 10.5 inches from the bottom. I have a 1.5 by 10 web at 5 inches from the bottom. Divide by the total area. I have a Y bar 7.65 inches as shown here. Now we calculate our moment of inertia. How many pieces do we have? Really 3. We have 3 pieces. 1, 2, and then these 2 wings can be lumped together. So I started with the wings, and then there it is, 2 times 1 times 3 to the third over 12, plus 2 times 1 times 3 is the area, times the centroidal distance is 9.5 minus 7.65 squared, plus my top flange is a 10 by 1 to the third over 12, and 1 times 10 times the centroidal distance squared, plus my web is 1.5 times 10 to the third over 12, plus 1.5 times 10 times the centroidal distance squared. All of that adds up to 337.4 inches to the fourth. So now we need to find Q. So A prime, in this case, it's a little different. It's not necessarily all the area above or below. That gets a little confusing because the shearing plane is vertical, not horizontal. So when the shear plane is vertical, now you're talking about the area of everything to the right of the shear plane or the area of everything to the left of the shear plane. Because you can kind of think about it is all the stress, the normal stress going in and out of the page in this area has to find its way to balance all the stress down here. Remember the flexural formula, everything above the dotted line is in compression. Everything below the dotted line is in tension from the flexural formula, my over I. So if everything above the line is in compression, everything below the line is in tension, then all this compression has to be balanced by this tension perfectly because the sum of the forces has to equal 0. So whatever stress is in this wing is compression. It's above the dotted line. So that compression is balanced by some of this down here in tension. And they have to basically, it's like matter and antimatter, they have to cancel each other. But in order to do that, you have this shear flow that goes across this plane. Does that make sense? Does that not make sense to anybody?
Could you maybe just like give a brief recap of what that was?
Okay. Anything that is a part of this section that is above the dotted line, the neutral axis, is going to be in compression. Anything that is below the dotted line will be in tension. And that's according to the equation my over I. If y is positive, then you have compression. If y is negative, you have tension. So this little wing right here is sharing some of the compression. And it's going to be balanced by some of this web down here in tension. Every little bit in compression is balanced by some little bit in tension, but they have to cancel each other. So this compression has to basically flow across this plane, and down into here to be canceled by some of the material in tension. It's a shear flow. Did that help or hurt?
I think it helped.
Okay. Well, let's work through the problem, and then we'll revisit it if it's still not clear. Okay. So we have to start by finding Q, and again, if the shear plane is vertical, then it's everything on the right or everything on the left of the shear plane. If we start with everything on the right, that's this hatched area right here. So the hatched area, A prime, is 1 times 3 inches squared. Y bar prime is still measured vertically. Don't try to start measuring this horizontally. It's the definition of the area is defined as on the right or on the left of the shear plane. But once you have this area, it's still the vertical distance from the center of the hatched area to the center or the neutral axis. So this distance, y bar prime, is 11, that's to the top, minus 1.5 inches to the center, minus the 7.65 to get me that distance right there of 1.85. So Q is 3 inches squared times 1.85, 5.55 inches to the third. That's Q. I can also find Q by taking everything to the left of the shear plane. Probably not my first choice, but you can do that. So if we do that, then what I can do is find the area of A prime is 1 times 3 plus 1 times 10 plus 1.5 times 10. Notice there's only one wing on the left-hand side, so 1 times 3. The total area of A prime is 28 inches squared. Y bar is going to be 7.65 minus the center of gravity of this whole thing. So the center of gravity of this whole thing is this expression here, which is pretty much exactly what we just did, only there's only 1, not 2 in here. And the total area is 28, not the, what was it, 31? So that equals 0.20. It's not very much because the difference in the center of gravity of the red area from the center of gravity of the whole area is not very different. Did I have a question? Okay. So that's what I'm showing right here. Y bar prime is this little sliver between the center of gravity of the red and the center of gravity of the whole thing. So Q is equal to the whole area times Y bar prime, 28 inches squared times 0.2, 5.57 inches to the third, which is very close to 5.55 inches to the third, accountable to round off air. So it actually works. And this is a great way to check your work, especially if something that could be as confusing as having a vertical shear plane. So let's find the maximum fastener spacing S. The shear flow Q is VQ over I. Again, we took out the B term to get the shear flow. So I have 700 pounds. Q is 5.55 over I was found to be 337.4. I have 11.51 inches or pounds per inch. Okay, this is now this inch right here. This inch right here is not the width of the shear plane. This is inches in and out of the page. So this 11.51 pounds per inch of beam along the span or in and out of the page. So fastener spacing S is equal to my F allowable over Q. My F allowable was 100 pounds as defined over 11.51 inches. And that gives me 8.69 inches. So my maximum spacing of my nailing can be 8.69 inches. I can go less, but I cannot go more. If I have a spacing greater than 8.69, then I will have a load per nail greater than 100 pounds. Okay, any questions on this concept?
So the spacing for the fastener is perpendicular to the shear plane that we're finding. You said it's in and out of the page, so
Yes.
that would be perpendicular to our shear plane, right?
Yeah. Okay, just a second. I want to make sure I answer this correctly. I'm talking about nails that look like this. Okay, so the nail is perpendicular to the shear plane. And that's what's keeping the two pieces from shearing across each other. Okay, the force that we're talking about, Q, is in the direction in and out of the page. That's the force Q. We're not talking about something that's trying to take these and vertically separate them. We're talking about something that's trying to shear them in and out of the page. So the spacing of my blue nail right here, that 8.69 inches, is measured on a coordinate system in and out of the page.
All right, thank you.
Okay, Okay. This is weird. Pardon me, having some technical interesting problems here. Okay, so we're there. Okay, so we're right there. Okay. Trying to get a handle on how many more we have. Okay. Oh, there's a bunch of chat there. Yeah, F allowable was given by the problem statement at the beginning of the problem. Yep. And Nicholas, the nail is in the side. Yes, just like I showed here, the blue nail is what we're talking about. And the spacing of the nails is in the direction in and out of the page. Okay, so that's along this little side plane right there. Now let's find what the maximum spacing would be at this shear plane here between the top half and the bottom half. So to do this, same procedure, but I need to find A prime. So A prime, if the shear plane is horizontal, then A prime is going to be everything located above or below the shear plane. Here, the shear plane was vertical, so it's everything on the right or on the left. Here, everything above or below. So starting with the top piece, A prime is, I have two wings, 2 times 1 times 3 are the two wings, plus the 1/10 top flange. So A prime is 16 inches squared. Y bar prime, you have to find the center of gravity of the red area. So I just did 2 times 1 times 3 times 9.5 is the centroidal distance, plus 10 times 1 times 10.5 is the centroidal distance over 16 inches squared. So this is the center of gravity of A prime minus the center of gravity of the whole section, and that is 2.48 inches. So from the center of the red to the center of the hole, 2.48. That makes Q 16 inches squared times 2.48 gives me 39.6 inches to the third. Now notice Q is so much larger than this Q. So you know the load is going to be much, much higher across this junction than this junction because Q is so much bigger. Now, if I find Q by coming at it from the bottom side, then the area of the web is 1.5 times 10 high. So A is 15 inches squared. And Y bar prime is the center of gravity of the whole thing minus the center of gravity of the web. And that gives me 2.65 inches is that distance right there. So Q is 15 inches squared times 2.65 gives me 39.75 inches to the third. Again, these two are nearly the same within round off air. So to find the maximum fastener spacing, Q is equal to VQ over I, 700 times 39.75 over 337.4 gives me 82.47 pounds per inch. Much, much higher than 11.51 pounds per inch. So my allowable fastener spacing S is equal to 100 pounds over 82.47 is 1.21 inches. quite a difference. I can't put my nails, and here I'll draw. We're talking about now nails that are going this way. And in the coordinate system in and out of the page, those nails cannot be spaced more than 1.21 inches apart, or you'll put too much force into each nail. Okay, so finished a little early, but I'm happy to answer questions. If I can get this thing back. Come on, buddy. There we go. Okay, happy to answer any questions that you might have on this horizontal shear. Just so you know, the next presentation is on combined loading. And I had already planned, it seems like we almost finished each lecture for like 3 lectures in a row. And we came up maybe 15, 20 minutes short. So I thought it'd be best today to just finish out this lecture, take as much time as we need, and then start fresh on Thursday with the next lecture, which is all about combined loading. So this is pretty much it for horizontal shear. Please make sure you read up the chapter. I think it's chapter 7. And, a week from Thursday is our next midterm. So if you had any questions about that, I can entertain those at this time as well.
I do have a question. So is combined loading going to be part of the next week's test, or is it going to stop till today's lecture, or when?
Yes, thank you. Thank you. Number 1 question every single time. I should play on Family Feud. Top surveys on the board. Number 1 question. Horizontal shear will not be on the midterm. Combined loading will not be on this next midterm. This midterm is going to cover, and I don't even remember which chapters now, sorry about that, but, oh no, I think I do. Chapter 4 was, chapter 4 was, what was the name for that? Uniaxial loading. So chapter 4 was uniaxial load, and we also had in there, we had thermal stresses, and we had indeterminate structures, right? So you had a bar wedged between 2 walls, and you put a load on it, or you changed the temperature, or you did both. You put a load and changed the temperature. And we had 2 techniques for solving for indeterminate uniaxially loaded members. So we didn't cover that on the first midterm. That will definitely be wide open for this midterm. We also then did chapter 5. Chapter 5 was torsion. And so for torsion, you had, I'm sorry, let me go back to chapter 4. Chapter 4 also covered axially loaded diagrams. So you have to be able to find the uniform load or the axial load diagram. Chapter 5 was torsion. So torsion, you have to be able to calculate the torsion, find your reactions, do a torque diagram, find the twist in degrees or radians from any point, and we had then indeterminate torsionally loaded members, which again had 2 methods for solution, the compatibility method and the flexibility method. So that was chapter 5 stuff. And then chapter 6 stuff included the biggie, the real biggie, really in my opinion, the biggest thing in this whole course is shear and moment diagrams, but it will also cover the flexural formula finding stress due to my over I. Excuse me, just a second. I'll be right back. Okay, sorry about that. All right, so any questions on what we're going to be covering? Well, we're not going to be covering biaxial bending. We did that before we did horizontal shear. So it will not cover biaxial bending, it will not cover horizontal shear, and it will not cover combined loading, which we're going to tackle on Thursday. But it does go chapters 4, 5, and 6 up to and including the flexural formula, my over I, or minus my over I. Anybody have any other questions for me? Everybody remember the format of how we do the test?
I was gonna ask you about that. You're gonna do the same format as that. We have to put in the answers in the, and then we upload the sheet, right? Like our work.
That's right. Yep.
For his next test, would you mind say that we can just upload our work? Because when I was, I don't know, it would get me nervous when I was putting in my answers, typing in my answers. So I don't know if that's fine with you.
Well, that's a good question. I would hold off on typing in your answers until, like that very end, maybe, so that you don't lose any time typing in those answers. But it's kind of like a fail safe. If I don't get your notes, if your notes don't upload or I can't read them, and that's really the big issue is uploading them, but I can't read them. You guys would be amazed at how difficult some of these are to read. So the thing about typing in the answers is that it's typed in. There's no way I can misread your answer if you type it in. So let me put it this way. If you do not take the time to type in your answers, then I only have one source. That's your uploaded work. And if I can't find the answer or I can't read the answer in your uploaded work, I have no backup. There's nothing else I can go to. But if you type in the answer, just the answer, m equals 36 kip feet, and then you upload the work, I have two things that I can compare to, and it's to your advantage.
Excuse me.
Thank you.
Can you provide some boxes? We just enter our solution or the final answer in it. I think it reduced time for us.
I'm not following your question. The exam is set up that has text boxes. You just click on the text box for problem 1, type in the answer. Click on text box 2, type in the answer. And then you upload the work. If you don't have time to type in those answers, I will grade it based solely on what you've uploaded. But if I can't read what you've uploaded, then I have nothing to go off of. That's what I'm trying to say.
Will it be like 3 questions again?
Yes, it will.
Has the test already been written?
No. I'm so far behind. Are you kidding? I'll write it like 20 minutes before I do it.
Oh boy. I have a question.
Yes.
So for the exam, we can still use our iPads, right? Like what I've been passing for my homework. Do I still need to take a picture or something like that?
Well, it's the same rules as test number 1. You should not have an iPad or a notepad or anything like that available for test security. And that's why everybody's got to be on Zoom. Everybody has to have a functional webcam to be on Zoom for test security. So I don't remember exactly what we said last time, but it's exactly the same as last time. The idea was that you have your laptop or your computer screen or whatever that has the test that you're taking on it, and you do all your work with pencil and paper and then upload that. You shouldn't have other electronic devices within an arm's reach for test security.
Okay.
Okay. Mustafa, did I answer your question? I feel like I left you hanging.
Yeah, I'm fine. Thank you.
Okay. All right. Anybody else? I mean, we still got 14 minutes or 9 minutes, 9 minutes.
Well, I have a question for the what we learned about just right now. For the S, it's the spacing between the nail, is that like
Yes, it is.
so if you're gonna draw let's say um your nail is gonna be at the very first into the page and then 8.69 into the page more.
Yes.
Does that make sense?
Yes.
Okay, that's the spacing between the nail. Okay, that makes sense.
Yes.
So
It-
whatever is the length of the beam, that's how many nails here. Like for example, that's how many nails are you gonna need? Something
Yes.
like that. Okay.
Uh-huh. Yeah. And it's also like if you have hired somebody to build this beam for you and you tell them, I want a beam made out of these pieces of wood and I want you to use these 10-penny nails. Well, the first thing the person who's going to be building that beam is going to ask you is, well, how many nails do you need? Or how far apart can I put those nails? And
Mhm.
then you're going to say, well, for the wings, let's put them 8.5 inches apart. But to connect the top to the bottom, they got to be no more than an inch apart.
Okay.
And
That
then,
makes sense.
so the person building was like, wow, every inch? Ooh, I better go buy some more nails.
Does that mean it's more stronger when you go push and pull, right?
Yes. Uh-huh.
Okay.
Okay. Any other questions? All righty. We will pick this up on Thursday when we talk about combined loading. And so I will see everybody in 2 days. Have a wonderful evening.
Thank you.
Thank you, Professor. You too.
Thank you.
Thank you.